Okay, so let's continue with our summary on um, equations, and now I want to discuss a little bit about differential equation. Okay, so just to recap what we saw before, we saw equation with numbers of this kind, we saw equation with matrices of this kind, and then we know how to solve them, or at least I'll show you some ideas on how to solve them. The target is a number or a vector, depending um, on the two cases. And we introduced the inverse matrix um, to solve the matrix equation. For a differential equation, the important thing to remember is the differential part, meaning that we are dealing with the derivatives. So we have a function of which we know the derivative. Okay, so we know the derivative of a function, which is g of x in this case, and we would like to understand which is f. Now, as you can see, it's not super straightforward to understand how to do this process, but if you remember videos on integrals and derivatives, we know the fundamental theorem of calculus, which states that if you have a derivative of a function and you integrate it, you get the function itself plus a constant. Okay, now this constant usually depends on the initial value of the integration and the final values as well. Okay, and we remember, so we can see that because the derivative is basically a variation in x, in f of x, over a variation of dx, integrated, so summed over a variation of dx. Okay, now hand wavy explanation that math would hate is basically you can simplify the dx because it's the same in both sides, and then you have a full variation of your function, which is in fact f of x1 minus f of x0. Okay, so you actually retrieve your function f of x by integrating your derivative. So this is cool, meaning that we can proceed further. And by the way, this is just to let you know that differential equations are basically anywhere in physics. Anytime you have something that varies in time, in space, in temperature, or whatever, you have a differential equation that allows you to solve for the particular problem. And when I will deal with some physics, we will go through some example and then we will see how to solve them. Just to let you know, there is no simple way to solve differential equation. There are many varieties of them that can be solved with the same techniques. I don't think I will go into go in details on that, but I want to give you some basic idea on how to approach it. The other thing that we need to remember is that a differential equation to be solved needs to have some properties, and we need to give the initial condition. As I said, the integral starts from one point to another, and that initial condition is very important to solve the equation. Also, we need to make sure the derivative of the function that we are looking for has some properties. So this function gx must satisfy some properties. For example, cannot grow too quickly, must be continuous, or things like that, in order to make sure that the solution is unique, because you want to find only one solution for a problem, ideally. So that would be the best case scenario. Okay, let's see if I can show you a couple of examples before I conclude this very brief introductory video, because I will go in detail when we will deal with some physics problems. But let's state these equations. So the derivative of f of x is exactly equal to f of x. This should ring a bell because if you remember, the derivative of e to the x is in the x is exactly e to the x. We know that. We proved it a couple of times already. But I want to be more specific because if you add a constant to e to the x, and if you add a number b, this still remains the same, because if you differentiate and you call this g f of x, when you take the derivative of this function you get the same function again, provided that you give some specific value on these two numbers. So that's why, for example, we can fix f in 0 and we want it to be 1. So in this case we know how to find the numbers, because f in 0 means b equal to 0 and a equal to 1, because a e of 0 plus 0 is equal to a, and if it's 1 we get f of 0 equal to 1, and then the derivative itself is the same. So this is our function basically, e to the x. Okay, not surprising, very dull example, but just to give you an idea that it can be sometimes easy to solve the equation if you know a little bit about derivatives, or if you guess the derivative right. I'm not saying that guessing is the correct way to do that. As I said, there are plenty of standard technique to solve equation if you are not considering numerical examples, because there are also equations that cannot be solved analytically or manually, and you have to go through numerical calculations with a PC, a computer, or a software that does it for you. But let's see an example. For example, derivative of f of x over dx is equal to x. So which is the function that when you differentiate it gives x. In this case we can integrate. So if we integrate, and then we need to go x f in 0, let's say equal to 1. In this case we integrate from 0 to whatever, and then we do d of x, and this is x squared divided by 2 plus a constant. Now we want to say that x squared divided by 2 plus c in 0 is equal to 1. So when we put 0 here, we have c equal to 1. Okay, so our function would be x squared divided by 2 plus 1, which when differentiated we get x, because we know that the derivative of x squared divided it's exactly 2x. So the derivative of x squared divided by 2 of x is equal to x exactly, because the 2 cancels out and the 1 gets removed because it's a constant. Okay, so in general it's not easy, it's not that easy to solve equation, and we'll see example of that. But yes, bear in mind that this is a very important piece of math, and there is a huge literature, fields of study. There are still differential equations that cannot be solved nowadays. So I mean, it's a huge argument to dig into, and I just wanted to give a snapshot of what it is. And this is just linear first order differential equation. We can deal with partial derivatives, higher order differential equation. So when you have, for example, equation like this, we will see them plus, I don't know, c equal gx. So when we have second order, first order, higher orders, and then there can be partial derivatives as well. When you have a function of multiple variables, x and y and z, but you only differentiate over x, because that's the only variable that changes, and then this is a function of x, for example, or things like that. I mean, I just use a funny symbol to represent the fact that we are differentiating over x and keeping these two numbers fixed instead. Okay, so this is all I wanted to say about differential equation. Remember that there is an integration that is taking place. There is an initial condition that it needs to be enforced, and then you find the solution is a function. It's not a vector, it's not a number. The solution of the equation is a function that will be the solution of your problem. Okay, hope you enjoyed. See you next time and have a good week.